Hello, everyone. Welcome to this collection of video lectures covering my doctoral research on a generalized voting game for categorical network choices. This project has been co-authored by myself, Yue Lin, my PhD supervisor, Stefano Nassini, and Martin Labe. This paper this is an ongoing project that started in September 2022 and led to the paper of this given URL. You can find it. The Python code for 3 different empirical applications are also available on GitHub from the given URL. And the paper has been presented at the following conferences at this time. So this video lectures is intended for a comprehensive guide to explain the whole paper as well as some part of the empirical application code and the proofs. So it is divided in a small chunk in a digestible way so that the notations and the proofs parts can be easily followed. Let me start with the main motivation of the project. So traditional econometrics approach for dealing with categorical data, since when we want to consider estimating a value or doing a statistics on sort of features, traditional methods such as logit or probability models typically has this assumption that the individual's outcomes are independent to each other. It means that each observation is treated as if it were isolated from the other observations. However, these assumptions often fails when we comes to empirical realities because the choices often shows structured pairwise dependencies on those categorical data. And once we acknowledge those dependencies, a natural representations just comes out. It is the network. So on the right-hand side, I'm showing you 3 examples of such pairwise dependencies. First, in geopolitics, countries tend to adopt their policy positions based on their allies' choice and opposed to their adversaries' choice. Their categorical choices, for instance, on the sustainability, migration, something like that, are not independent features. Secondly, in social networks, adolescents' behaviors such as like smoking, drinking are highly influenced by their peers. So in this case, the decisions of individuals propagate through the connections, through their friendship networks. The third examples in market competitions, firms, enterprises imitate competitors' successful products. They want to deliberately differentiate their products from the adversaries. Again, in this case, product features are interdependent between those individuals, in this case, the firms. So the main takeaway is that when categorical outcomes has these structured dependencies, we should model them explicitly as a network interactions. So this motivation highlights the need for a framework that can capture those different points that are interdependent categorical choices rather than treating them as individuals' observations or independent events. When it comes to networks and estimations or data classification, those 3 common framework arises. So we got on the first hand, the data classification where you know the network, you want to predict the outcomes of an individual. The secondly, there's the network propagation where you got some choices inside the network and you want to know how does this choice affect other individuals' choices? How does this choice spread or propagate through the networks? The third the third case is network discovery, where the choices are already observed And what you want to do is to infer the network structure between those individuals. These three tasks uh, are treated differently and in isolations, mostly in the literatures, but these tasks can be seen as differing only on what is taken as given and what is taken as inferred. So whether the network structures or the choices, which ones are given and which ones are inferred. For the current approaches that pre-exist and it can be served as a inspiration point for our voting game models, we can look at those three different branches. On the first hand, the data classification, we got space-time autoregressive models that can tackle those cross-sectional dependencies and patterns, basically doing a autoregressive model, but consider the extra dimension of the space. The secondly, we got network propagations. There are a tons of influence diffusion models, such as linear threshold model, where inspired by the neural network, you accumulate the influence from your neighbors. And once the influence surpass a threshold, you become sort of activated by those influences and you become your choice shift. The other very similar approach is the independent cascade model. Instead of calculating the threshold, it is a probabilistic approach, but achieving the same thing as studying how choice propagates through the networks. So they are behavior spread simulations approaches. Finally, in terms of network discovery, we can use different methods such as network lasso or categorical regression to infer links from the choices. So in summary, those existing models excel in those specific tests, but none of the models provide a uniform behavioral micro foundations linking those classification, propagation, and network discovery. So in this paper, what we trying to do is to provide a game theoretical micro foundation to all these three aspects. So let's talk about the network, since this is a starting point. We consider two type of relationship. We can be attractive relationship or repulsive relationship. Since we established that individuals perceive a gain when the individuals made choice that is consistent with their environment, or we can say we're matching attractive neighbors, and it perceived as a loss if the individual match their repulsive neighbors. And based on that, our framework yields two complementary games on the same mechanism, differed only on what is given and what is considered as to be inferred or to be predicted. We got direct voting game, where we got network structure is given. We know the network. We are trying to infer the choice. We got also the inverse voting games, as the name suggests. You have, on the other hand, the choice are observed and you want to discover the network. So one is considering classification or network propagation. The other is network discovery. And the classification can be thought of as a problem of reaching a Nash equilibrium. After we will see that in the following lectures we'll define a utility functions. When the Nash equilibrium arrives, then this is considered as the classification result. And this can be also generalized to cover some machine learning algorithms such as k-nearest neighbors, as we will see in the subsequent lectures. In the next module, lecture 2, we will going to talk about more details in the settings of the notation of the sets that we're talking about, the setting of the problem. Thank you very much for watching, and see you guys in the next lectures. Bye bye.